Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who are nominated to speak by their senior colleagues. Today, we have David Bartusel, who is a PhD student of Hartmut-Fuhr at RWTH Aachen. We are happy to have him here today to tell us about the role of connectedness in STFT phase retrieval. Take it away, David.
Yeah, thanks for the introduction, and of course also for the opportunity to speak here at Codex. As you've already been told, this talk is going to be about phase retrieval, and particularly about phase retrieval for the short-time Fourier transform. And the point I want to focus on is about which signals can be reconstructed by using which windows for the STFT. And then we will see what connectedness has to do with all of this. And in order to start, we should, of course, take a look first at the problem itself. So I'll spend the first few moments explaining what the problem is about. And I guess the best way to introduce a problem is to start by a real-world application. And in the case of STFT phase retrieval, one of the major applications would be tychography. And in this problem, we are given some object, which we want to analyze. And in order to analyze this object, we shoot, for example, some X-rays at the object. And these X-rays will get diffracted by the object. And we can measure these diffracted rays on some screen that we put behind the object. And on this screen, these diffracted rays will form a so-called diffraction pattern. And what we, of course, will only measure is the intensity with which these diffracted rays will hit the screen behind the object. And maybe this is not enough information to recover all the information we want to obtain about the object. So in order to not obtain only one measurement, but multiple measurements, we can insert a filter between the X-ray source and the object. And if we move this filter around into different positions, then we will obtain multiple measurements, which hopefully will help us recover the object. Okay, so mathematically speaking, let's say the object is modeled by some signal function f, and the filter is modeled by some window function g. Then what we can measure on the screen, at least if the screen is put far behind the object, is the following. So we have pointwise products of f with shifted versions of g, which makes sense because kind of the information of the object which rests in place will be combined with the filter which is shifted around. And then of these pointwise products, we will take the Fourier transform. And then, as I already said, since we can only see intensities on the screen, we will only obtain the absolute value of this Fourier transform. And in short, this can be noted as the so-called short-time Fourier transform VGF. So short-time Fourier transform of the signal f with the window g. And as you can see, this is a function of two variables, where x, as I said, is the shift variable, and omega will be the frequency variable, because for every shift we compute a Fourier transform, and this Fourier transform is then the function of one frequency variable. And of course, I didn't tell you so far where f and g live, so what the domains are. I'll come to that in a moment. But to recall what the problem really is that our goal is, and this is called phase retrieval, for some fixed filter g, which we usually know what the filter is. We want to recover the signal f from the measurement VGF absolute value. And maybe to put some context around this, for some of you, the word spectrogram might be familiar in this setting. So the squared measurement is usually referred to as the spectrogram in the time frequency community. So maybe this helps putting things into context for some of you. So the first thing that happens, or that maybe pops into our eye when we are looking at this phase retrieval problem, is that the STFT is, of course, linear in f. So if we multiply f by some constant, then we can pull out this constant out of the VGF. And because of the absolute value, if this constant has absolute value 1, then we won't see any difference in measurement. So if we multiply f by a constant of modulus 1, then we won't be able to distinguish this measurement from the original measurement. And so the best we can basically hope for is to recover f up to the identification f identified with gamma f, where gamma is some complex number of modulus 1, and the set of complex numbers of modulus 1 we shortly write as the torus. Okay, now I promised you to tell you about the domains of f and g, and there are multiple settings which we can consider. And I brought you 3 settings, which are basically the most important ones. So the first thing would be probably the most accurate model. So we would take f and g to be functions, L2 functions on a continuous domain, for example, in this case, L2 functions on RD. And then, of course, from a more, let's say, computational standpoint, we should go ahead and maybe discretize these signals, and we can consider little L2 sequences f and g on Z. And if this is not enough, then we might also go to a finite dimensional setting where f and g are just vectors in CD. And as I started looking at this problem, I looked at these 3 settings and I thought, well, maybe let's start with the finite dimensional setting. Then f and g are just vectors. The information I want to recover is just finite. Basically, what can go wrong? But the longer I looked into the problem, I realized that actually the first 2 settings are the ones that behave better, let's say. And also the first 2 settings, so the L2 of RD and the little L2 of Z, they share a lot of similarities, whereas the finite dimensional setting behaves a lot more pathological. And so today we are only going to look at the first 2 settings, and I won't tell you a lot about the finite dimensional setting, because not only the proofs but also the results are a little more involved. And yeah, I'd say the basic things that happen are best visible in the infinite dimensional settings. Okay, so now that we know what our problem is and where our functions live, we would like to have a main idea how to tackle this problem. And the main idea for STFT, phase retrieval, usually comes by the following equation. And honestly, this equation is not quite accurate here on the slide. For it to be accurate, you would have to add some constants and make some variable flips. But this version here, which is on the slide, just captures everything you need to know. And what you need to know about this equation is that the left-hand side only depends on our measurement. So what is on the left-hand side is just the Fourier transform of the spectrogram. And so this is information we can access by our measurement. We might not want to compute this explicitly, but this is something we have access to in theory. And then on the right-hand side, we have a certain decomposition into 2 factors, where the first factor just depends on the signal f, which we want to recover. And the second factor only depends on the window G, which we know what G is. So what we basically would like to do is to solve this equation for VFF, because this is a part we don't know anything about so far. And this is the part which essentially captures the information about F. And in order to solve this equation for VFF, we have to divide by VGG, which of course is also only possible when VGG is non-zero. And so from this standpoint, phase retrieval kind of becomes a sampling problem. So we can rewrite this as a sampling problem as to recovering F, again, up to global phase vector from VFF on the support of VGG. And the nice thing about VFF is that if we would know VFF on the whole domain, so let's say if VGG was non-zero almost everywhere, then it is known that we are actually able to recover F up to a global phase vector. So if we take a window such that VGG doesn't vanish almost everywhere, or vanishes almost nowhere, then phase retrieval is possible for every single signal. Okay, so this will give us a first idea on how to choose a filter. So we see this condition is a nice condition to have. and will just enable us to do phase retrieval with whichever signal we want to. And in order to illustrate the choice of the filter even more, I want you to look at the following situation. So imagine we are some physicists and we want to perform our experiment. We have some object. Now we need to choose which filter we will use to perform our measurements. And let's say we have a whole bunch of filters in the box in front of us. So let's just think of this as this box contains all infinitely many filters that there exist. Now, if we don't have any idea which filter to choose, we might just as well just pick one of these filters randomly. And the good thing about this, at least in the finite dimensional setting, is that it is known that with probability 1, we will obtain a window which actually has the property that VGG vanishes almost nowhere. So if we have a box of infinitely many filters, so a box of every filter which exists, then we can just pick one filter at random, and we are pretty much guaranteed that we can just do phase retrieval with this filter. And this is good news, right? So at this point, one could say, okay, I'm satisfied here. I know everything about theoretical recovery, and now I can turn to something like finding efficient ways to actually recover the signal numerically. But I am not satisfied at this point, and I want to show you why by looking at another situation. So let's say there's a different physicist, maybe from not such a rich institute, and they walk into their office and they have only just a few filters to choose from. So if they just pick one of these 4 filters, let's say at random, then they obviously won't have any guarantee that VGG will be non-zero almost everywhere, so they won't have any guarantee that phase retrieval will work with this randomly picked filter. So in this case, we are actually forced to look at phase retrieval with a fixed filter. And you could argue now that maybe this institute is not so clever for having a bunch of filters which are really bad, because as we saw above, just basically most of the filters work in every situation. So there are a lot of filters which just work universally. Why does this institute just have 4 filters that are bad? Well, of course, there are nuances to that. And maybe these filters which work universally are just hard to produce or expensive to produce, so not everybody will have access to them. Or, as I hinted at before, there's also, of course, the aspect of numerical recovery of a signal. So maybe there are some filters which are very good for theoretical recovery, but would perform badly numerically. So there are multiple reasons why we might not be able to just use one filter that works universally. So we kind of have to adapt our choice of filter on the kind of signal we have. And well, you can argue again now, we want to know what the signal is. So how can we choose the filter based on the signal? Well, of course, we cannot choose the filter based on the exact knowledge of the signal, but usually we won't just walk into our office and find some random object there, which we don't know anything about, but usually we kind of know roughly what this thing is, and we just want to analyze some details of this. So if we know that our signal has a certain structure, then we might just pick a filter which is suited very well for analyzing object of this certain structure. So this is kind of the motivation I wanted to give you, why I look at this problem, and why I don't want to use a random filter, but just want to analyze why or what signals can be recovered using what filters. Okay, and as we will start in the discrete setting, and by discrete setting, I will always mean the infinite dimensional discrete setting today. So as I told you before, this is the case where f and g are little L2 sequences on Z. And before we go into details here, I want you to show some examples of problems that can occur with phase retrieval. And for example, I brought you this signal where the black bars just represent non-zero entries of f. And let's pair this signal with the following window. So, of course, in the current position of the window, if we just take pointwise products of f and g, then this pointwise product will be 0, right? Because f and g just don't overlap. So if the pointwise product is 0, we won't measure anything. Now, if we start sliding this window to the right, of course, the pointwise product will not be 0 anymore, and our measurement will start picking up something, and we might just pick up even more with the next position, and so on and so forth, until the window is positioned in between of these two sections you can see of the signal. And again, at this position, the pointwise product will be 0. Okay, and then if we shift the product further to the window further to the right, then we will start picking up, let's say, the right part of the signal, and then maybe more of it, and so on and so forth, until maybe we run out of this the support of the signal, and again won't measure anything. So in order to see what happens here, let's return to the state where the window is positioned in between of these two sections of the signal. And what we just saw is that the left part of the signal can only be measured when the window is positioned to the left of the current position, and the right part of the signal can only be measured if the window is positioned to the right of the current position. So what we can identify is, let's say, a red and a blue part of the signal, and no entry from the red part will ever be measured simultaneously with any other entry from the blue part. So what this basically means is that we cannot relate any information from the red part to the blue part through the measurement. So we have some measurement which just captures what happens in the red part, and some part of the measurement which just captures what happens in the blue part, but there's no way to put these information together in order to actually recover the whole signal. And mathematically, what happens here is we can decompose f into a signal, in the sum of two signals, f1 and f2, where the short-term Fourier transforms of f1 and f2 have disjoint support. And in this case, it is clear that f1 plus f2 and f1 minus f2 will, of course, have the same absolute measurement. So what we did here is basically just flip the sign on the blue part while leaving the red part as it is. And this emphasizes the fact that we can basically get the global phase on the red part and get the phase on the blue part, but we cannot see how the phases interact with each other on the red and the blue part. So f1 plus f2 and f1 minus f2 are in this case two signals which do not agree up to a global phase vector, but agree in absolute measurement. So phase retrieval is not possible in this case. And what we can see in this example is, of course, that this problem is caused essentially because the window is just not wide enough to bridge the gap between the red and the blue part. So if the window were wider, let's say one entry to the left and to the right, then there would actually be a position where we could measure red and blue together. But in this case, we could say the red and the blue part are too far away from each other for the window to bridge the gap between these two. Okay, before I go, I'm going to explain this in details. I brought you another example. And in this example, the signal looks better, right? So there's no physical separation of two parts of f. And in fact, if we would use the window on the left side, phase retrieval would work in this case. But in this example, we consider a different window. So at the current position of the window, we can only pick up the second, the fourth, and the sixth entry of f. If we move this window one spot to the right, we can only pick up the first, the third, and the fifth. And then again, if we move the window one further spot to the right, then we can just measure the second, the fourth, and the sixth entry, and so on and so forth. So again, we basically have the same situation as before. We have a red and a blue part, and no entry from the red part can ever be measured simultaneously with any entry of the blue part. So this is exactly the same situation of the decomposition into a signal f2 plus a signal f1 plus a signal f2. Only in this case, it might just not be visible as quickly as in the first case. But in both cases, you would agree that there's a certain disconnectedness in the support of F that causes trouble with phase retrieval. So what we can see with these examples is that disconnectedness causes problem with phase retrieval, whatever disconnectedness means, but we will see that on the next slide. And the question I want to answer today, or partially answer today, is whether there's also the other statement, so the converse statement, that having connectedness in the signal guarantees phase retrieval. So what I want to seek today is finding windows G such that connectedness implies recovery of a signal. So this means a signal F can be recovered up to a global phase factor by the absolute STFT measurement if it is connected in the sense that we're going to define on the next slide. So this is the goal of the talk. Okay, in order to define what connectedness means, let's look at how the STFT looks like in this setting. And you might realize that I exchanged the variables here. And I did this just to make clear where these variables come from. So I replaced X by K and omega by Z. And as F and G are little at2 sequences in this setting, it is clear that K, which is the shift parameter, also needs to be an integer. So this is the main reason why I changed these variables. And then we take the Fourier transform on Z, and the frequency domain for Z, or let's say the dual group of Z, is the torus. So our frequency variable will be a complex number of modulus 1. And this already shows us why phase retrieval might be maybe the easiest of these of the three settings here, because what we have is an L2 sequence F, which we want to recover. So there's just a countable number of entries we want to recover. So this is just a countable number of complex numbers we want to recover. But our measurement, since the frequency variable is a continuous one, we actually have access to uncountably many measurements. So we kind of have some head start here by having a lot more measurements than entries to recover from F. Okay, and now in order to define what I mean by connectedness, we can look at the following set DG, which just contains differences between every two entries which are in the support of G. And how does this set help us to characterize recovery or connectedness at first? Well, let's picture the setting of the last slide where we have a signal in the first row and the window in the second row. And let's say there are two entries of a signal which we want to measure at the same time. So what this means that there is some position of the window where there are exactly two non-zero entries of the window aligned with these two non-zero entries of the signal, which we want to measure at the same time. So what this means is exactly that two entries of the signal can be measured at the same time if and only if their difference is in this set DG. Okay, but as we saw before, it is also important not only for two signals, two entries to be measured at the same time, but of course, how we think of this is if we can measure entry A and entry B at the same time, we can think of this as entry A and B communicating somehow. So we can relate some information from entry A to entry B. And now if we are able to relate information from entry A to entry B and relate information from entry B to entry C, then of course we are also able to relate information from entry A through B to C. Okay, so what we really need for connectedness or connectivity is the following. So I call the signal F connected if its support is connected with respect to the translations in DG. And what I mean by that is that I can take every two signals in the support of F and I can form a path within the support of F from one entry to the other by only using step sizes which are in DG. And now, just basically using the same counterexamples as we had on the last slide, it is easy to show that in order to have phase retrieval, the support of my signal needs to be connected. So if there's disconnectedness, there's no chance for phase retrieval. But as I told you, this is not the interesting implication. The more interesting implication is if connectedness is also sufficient for phase retrieval. And as for that, I want you to look at the following result by Rima Alefari and Matthias Wellershoff. This result was formulated actually not in this setting, but in the finite dimensional setting, and also for some special case of the set DG. But since the proof is essentially just the same, I think this is the right reference here. And what the theorem states is that basically if we are in the best possible case with G when considering DG, and I will explain later what this means, if we are in the best possible case, then recovery is actually equivalent to connectedness. So if signal F can be recovered up to a global phase vector from the absolute STFT measurement, if and only if its support is connected. And what I mean by being in the best possible case is best understood if we just go back to what we had in the beginning. So the very, very best case for phase retrieval would be that VGG would just be non-zero everywhere. Okay, so if VGG is non-zero almost everywhere, then phase retrieval is always possible. But if we take into account the set DG, then of course, if there is some shift which is not in DG, then VGG for this shift will just by definition of DG always be zero for every frequency. So the best chance, if we already computed the set DG and acknowledge that this might not be everything, then the best chance we have is that VGG is at least non-zero for shift parameters which are in DG, but then for all frequencies or almost all frequencies. Okay, and I also want to quickly go into the proof. So if we recall what our intermediate way of doing phase retrieval is to recover F from VFF on the support of VGG. So the support of VGG is now given very clearly in the assumption. And of course, what we only want to sketch here is the implication that connectedness implies recovery, because the other implication is more or less trivial. So let's say our signal is in fact connected, and we have access to VFF on the whole support of VGG, which is just DG times almost all of the torus. And in order to start, we can observe that there's one shift, which is, at least if the window is non-zero, which we are going to assume, there's one shift which is always in DG, and this is the shift 0, because if there's one entry in the support of G, then the distance of this entry with itself is just 0. So what we have access to is basically VFF with shift parameter 0. And if we look at the definition above of VFF, or the formula for VFF, is that VFF with shift parameter 0 is just the Fourier transform of the absolute value squared of F. So by Fourier inversion, we are actually able to recover the absolute value of F. And by that, of course, we can also recover the support of F. Okay, and now that we know the absolute value of F, all that remains is basically to recover at each given entry what phase belongs to this absolute value. And since we only need to recover this up to a global phase vector, we can just pick one non-zero entry and choose a phase for this entry as we want it. So at one entry, when we can just freely pick our phase. And then all the other shifts in DG come into play. So what we can recover with using shifts K non-zero is pointwise products Fj times Fj minus K. And by using these pointwise products, we are able to propagate the phase from some entry Fj to the entry Fj minus K, or the other way around. And since we assumed that the support of F is actually connected, this means that starting at one given entry where we chose the phase, we can just walk around the support by using just these shifts in DG and relate the phase starting from this one entry to all of the support. So this is the strategy how we can recover the signal and the phases, especially when we are in the best possible case where VGG is non-zero almost everywhere on DG times the torus. Okay, and starting with this theorem, one can basically ask two questions now. So the first question would be, well, is this assumption the best assumption, or is this assumption necessary essentially, or can we relax this assumption and maybe just need to assume that VGG is non-zero on some smaller set? Or the second question would be, and this is the question we're going to look at today, is which windows actually are in this best case scenarios. So are there maybe a lot of windows and a lot of practical windows which already fulfill this assumption? And of course, this would mean that for these windows, recovery would be equivalent to connectedness. Okay, and the easiest window class maybe we could think of would be compactly supported windows. And for compactly supported windows, we can take a look at how VGG looks like in this case. And you'll notice that I put a Z bar in here, but this is basically only there for making the formula look nicer. And since we are going to just look at or count the number of zeros of VGG on the torus, and the torus is of course invariant under complex conjugation, it doesn't matter if we put a Z here or a Z bar here. Okay. So what we have for VGG is, of course, since the window is compactly supported, we will obtain a finite sum. And with this finite sum, what kind of finite sum is this? Well, what we can see is this is a polynomial in Z. And now I already told you what we're going to estimate was the number of zeros of this function on the torus. And of course, since we have a polynomial, we know pretty well how zero sets of polynomials behave. Namely, if this polynomial is non-zero, then it will not have too many zeros. And of course, then this is again how the set DG is constructed. If we now take a shift K, which is in DG, this means that at least one of these coefficients is in fact non-zero, because this was just the definition of DG. So if we take a shift which is from DG, then this polynomial will not be zero. And this means that there are only finitely many zeros, and particularly only finitely many zeros on the torus, which means that VGG is non-zero almost everywhere on DG times the torus, which means that for compactly supported windows, in fact, recovery of a signal is equivalent to connectedness. And now maybe if we take this signal, this window to be exactly supported in the interval from 0 to L, then we can easily show that connectedness is just characterized by having holes of length L within the support of F. So if the support of G is exactly the interval from 0 to L, a signal F can be recovered by the phase retrieval measurement if and only if it doesn't contain any hole of length L in the support. And one thing I forgot to mention is I only talked about compactly supported windows, but here on the slide I fixed support to an interval starting at 0. But this, of course, doesn't matter because I can slide, the window gets slid out around anyway. So it doesn't matter if I fix this support to the interval from 0 to L, or it's just some other interval of finite length. Okay, so now that we know how compactly supported windows work, because compactly supported windows produce polynomials as VGG, we could wonder, okay, what would be the next best generalization? And the next best generalization for polynomials are power series. And how could we possibly obtain a power series? Well, let's assume that the window or the window support is limited to one side. So again, I just put the non-negative integers here on the slide, but the only thing that matters is that the support does not extend to both plus and minus infinity. So as I told you before, in this case, VGG will not be a finite series or finite sum anymore, but an infinite series. And in fact, this is a power series. And this is the point where complex analysis will enter the picture. And complex analysis, as many of you probably know, is a very heavy tool in phase retrieval. So if we just randomly grab one paper that's just concerned with phase retrieval, especially with STFT phase retrieval, there's a pretty good chance that complex analysis is there at some point. And complex analysis and power series, what we can think of this is, of course, that power series will define holomorphic functions on their disk of convergence. So in this case, since the window G is an L2 sequence, we know at least that the radius of convergence is at least 1. So this power series defines a holomorphic function on the unit disk. And there's, because of the decay of the coefficients of the window G, we know a little bit more, namely, we just even know that the function defined in that way is also in the Hardy space H2 of the disk. And the nice thing about Hardy spaces is that basically some properties of the holomorphic functions will carry over to the boundary. So what we know is that we have a holomorphic function on the unit disk. And again, if we choose the step size, the shift parameter k, to be in dg, then this power series is not identically 0. So we already know that there are, because of the identity theorem, not too many zeros in the interior of the unit disk. And then because of the properties of this Hardy space, we can actually conclude that VGG is again non-zero almost everywhere on the DG times the torus. So also for these one-sided windows, we know that recovery is actually equivalent to connectedness. And of course, what we can do is look at any window where the support is exactly the non-negative integers. Then we can see that DG is in fact everything. So every L2 window G, which support is exactly the non-negative integers, will do global phase retrieval for every signal F. So this is one corollary you could take from this. So before we make a theorem out of this, let's look at an even more general case. And in general, of course, the sum will span from -infinity to positive infinity. And we will no longer have a power series, but a Laurent series. And Laurent series and complex analysis also work well together. But in this case, since we only know that G is a little L2 sequence, this Laurent series might only converge on the torus itself and not on any open domain. And if this is the case, I don't know what to do. So these results won't work in this case. But we can try to extend this holomorphic function or this Laurent series to converge on an open domain. And how we can do this is basically just equivalent to making this Laurent series converge on some open domain around the torus, is to assume exponential decay. So what I just mean by that is that the series still converges if I weight it with some positive exponential. And with this assumption, we can show that VGG actually extends to a holomorphic function on some neighborhood of the torus. And now we again have a holomorphic function, which is not identically 0 if we take our shift k to be from dg, because then one of these coefficients won't be 0. And if we have a compact holomorphic function on a open domain around the torus, and the torus is of course a compact set in this open domain, then we know that holomorphic function can only have finitely many zeros on compact sets, which means again that VGG is non-zero almost everywhere on DG times the torus. So we basically identified two huge classes of windows where recovery is equivalent to connectedness. And this is the following theorem. So if I take my window G to be either one-sided or of exponential decay, then a signal F will be recoverable from the absolute STFT measurement if and only if its support is connected in the sense we had on the second two previous slides. Okay, and what I really like about this result is that the condition is very easy to check. So in order to check if a signal is connected with respect to a certain window, the only thing I need to look at are the supports of F and G. So there's no computation of any Fourier transform or short-time Fourier transform involved to check this condition. The only thing I need to know is the support of F and the support of G. And then I need to compare these in a certain way. And then I can basically understand if F is phase retrievable or not. Of course, G has to belong to these classes. So maybe I need to check if G does in fact decay exponentially. But this is just something, again, which involves not the support only of G, but only the absolute value of G. So This is, again, not much we need to know. And this is what makes this criterion very easy to check. Okay, so for the last few moments, I want to go to the continuous setting. So what we are going to look at here are L2 functions on R. So I just restricted myself to one dimension for this talk. And in this case, the short-term Fourier transform is, of course, no longer a sum, but an integral. And in this case, since the domain is R, our shift parameter will be a real number. And of course, the Fourier transform of a real valued, or the frequency domain of the real line is again the real line. So our frequency variable will also be a real number. Okay, and then we can almost define connectedness in the same way as before. The only thing we need to be a little careful about is how we define the set DG. But this is essentially the same as before, just in a globally formulated sense. So if we would use this definition for the discrete setting, we would actually obtain the same. I just had it written down for the discrete setting in a pointwise notation because I thought this would be more intuitive. But because we are looking at L2 functions here, we can no longer work with a pointwise version, but need to take, in this case, just the shifts, the set of all shifts, such that G times the translated version by X of G is not identically 0. And then connectedness can just be defined in the very same way as before. So we're looking at the L2 support of F, which is then some fixed set, and then we can decide whether we can walk around this set by only using step sizes which are in DG. And what we, of course, would like to have is the same start as in the discrete setting. And this was basically the following theorem, which also works in the continuous setting. So again, if we're in the best possible case for VGG, so VGG is non-zero almost everywhere on DG times the real line, then again, recovery will be equivalent to connectedness. And so this is basically really the same copy-pasted theorem as from the discrete setting. The only difference here is that the proof is much more involved. So basically what we did before was we recovered the absolute value of F, and then we fixed the phase at one given entry, and then we propagate the phase from point to point. And of course, we cannot do this any longer in this continuous setting, because fixing a phase at a certain fixed point will not give us any information, because pointwise information is useless in an L2 sense. So we kind of have to fix the phase on the set of positive measure and then propagate the phase from sets of positive measure to other sets of positive measure. And this is why I just put the proof is a lot of measure theory on this slide. And I don't want to get too involved in this. But you kind of understand, I guess, that the idea is still the same. We only need to replace pointwise information by information on positive measure sets. And this becomes a lot more involved, but the idea is still the same. And what we'll also see is that the same question I asked in the discrete setting, so which windows actually work for this condition, the analysis of this is actually very similar to what happened in the discrete setting, and you will see this in a moment. So the first thing we looked at in the discrete setting were compactly supported windows, but then this was just a special case of the one-sided windows. So let's start with the one-sided windows also in the continuous setting. And in the continuous setting, complex analysis will help us again. And in this case, complex analysis will come at the hands of the so-called Paley-Wiener theorems. And these theorems basically tell us about holomorphic extensions of Fourier transforms or short-term Fourier transforms of some L2 functions. And in this case, if we have a one-sided function, one of these Paley-Wiener theorems shows that the short-term Fourier transform will extend to a holomorphic function on the upper half plane. And again, this is not only some or not only any holomorphic function on the upper half plane, but it's also an element of the Hardy space, and this time H infinity of the upper half plane. But now we are in this very similar situation than before, because in the discrete setting, if you recall this, we had a holomorphic function on the torus or on the unit disk, and the frequency domain we were interested in was the torus. So this was the boundary of our domain of the holomorphic function. And in this case, we have a holomorphic function on the upper half plane, and the frequency domain is the real line, which is again the boundary of the domain of this holomorphic function. And then the properties of the Hardy spaces will ensure us again that VGG is in fact non-zero almost everywhere on DG times the real line. And so in this case, we are in the good case. So one-sided windows actually allow phase retrieval to be characterized equivalently by connectedness. And the last example, of course, is the counterpart of the exponentially decaying windows, which can just be defined basically in the same way as before, just replacing the sum by an integral. And in this case, there's another Paley-Wiener theorem, which tells us that VGG will extend to a holomorphic function on some strip in the complex plane, and this strip will contain the real line. So what we have here is a holomorphic function on some neighborhood of the real line, which is our frequency domain. And this is again very similar to what we had in the discrete setting, where we had a holomorphic function on some ring around the torus. And then we knew, since the torus is compact, there are only finitely many zeros on the torus. And of course, the real line is not compact, but what we still know about holomorphic functions, which are non-zero, again, this function is non-zero if x is in DG, then the zero set of the holomorphic function may not have any limit points on the real line. And this means that the zero set on the real line is at least countable. So VGG is again non-zero almost everywhere on DG times the real line. So with both these example classes of windows, we are again in the good setting where we can state the following theorem. So this is really just copy paste. There's nothing which is different to the discrete version. If we have a window which is one-sided or of exponential decay, then phase retrieval can be equivalently characterized by connectedness of the signal. And again, this is a neat condition because this criterion only depends on the supports of F and G. Okay, and now I'm going to wrap things up and summarize what we did today. So what we realized very early was that disconnectedness in the signal will cause, will inevitably cause some problems with phase retrieval. And then the question was, can we overcome these problems by just making the signal connected and basically not doing anything else? And the answer is, for some windows or for many windows, this actually works. So for these windows, connectedness or missing connectedness is the only obstacle for phase retrieval. So by just having connectedness, phase retrieval will always be possible for these windows. As I pointed out before, this characterization is nice because it doesn't involve, checking this, the assumption does not involve any computation of any Fourier transforms or short-time Fourier transforms. We can just work with the support of F and G and decide whether connectedness holds or not. And then returning to the applications, we can now use a broad knowledge of our signal F, so some rough structure we know about F, in order to pick a filter which is perfectly suited for our experiment. Okay, so to end things, I will give you the paper which is accepted for publication in JFAA and should appear there soon. You can also find the preprint version on the archive already. All of the results which I discussed today are both in the paper, of course, and in the preprint. And there are also, of course, some other results in the paper, namely also the result for the finite dimensional settings. And with that, I'm going to end and want to thank the organizers again for letting me speak here. And I want to thank all of you for your attention. And now I'm happy to take your questions.
All right, thanks, David. Let's all thank our speaker down here. Oh, I almost raised my hand. I'm going to clap instead. And I think we can stop the recording, Dustin.